Hello, everyone, and welcome to Kognito Key. Today, we're diving into a really massive challenge in digital communication. So, picture this. You've got a satellite beaming data straight down to Earth. But during that transmission, the message signal, which, is made up entirely of ones and zeros, can super easily get corrupted by noise or interference along the way. Which brings us to a pretty critical question. When that data arrives all corrupted, how do we not just detect the error, but actually fix it right there at the receiver? Like without having to go all the way back and ask the sender to retransmit the whole entire signal. Well, enter Hamming codes, invented way back in 1950 by the brilliant R.W. Hamming. This mathematical tool packages our data into blocks to act as the ultimate safety net. It uses redundant parity bits to brilliantly detect up to 2-bit errors, and, get this, it can perfectly correct single-bit errors right on the spot. Section 1. Encoding, the step-by-step process. Let's just dive straight into how this brilliant encoding actually works. So there are 3 really straightforward steps to encode our message at the transmitter. First up, we calculate exactly how many redundant bits, we call these parity bits, that we need for our message. Second, we position those parity bits at very specific spots, specifically at powers of 2 within the sequence. And third, we figure out their actual values based on whether we're going with an even or an odd parity scheme. Let's break down this powers of 2 rule using a simple 5-bit message, 1, 1, 0, 1, 0. Now, based on the Hamming formula, a 5-bit message needs 4 parity bits, which gives us a 9-bit sequence in total. Notice how those parity bits, the ones marked with a P, are placed exactly positions that are powers of 2, so positions 1, 2, 4, and 8. Then our original data bits, marked as D, just kind of slide in and fill the remaining gaps at positions 3, 5, 6, 7, and 9. Okay, but how do we actually determine the value of those P bits? We use what's called an even parity check, along with this incredibly clever take and skip logic. To find P1, we check specific data bits in a take 1, skip 1 pattern. For P2, we take 2, skip 2. You see where this is going, right? We're basically just checking to make sure the total number of ones stays an even number. If the count of ones is already even, boom, the parity bit is 0. If it's odd, the parity bit becomes a 1 just to balance the whole thing out. And here we have it, our final encoded sequence perfectly ready for transmission. Reading right to left, we've got 11101000011. Those carefully calculated parity bits have completely locked our original data safely into place. Section 2. Decoding, spotting the error. Let's shift gears now to the receiving end and imagine some pesky noise has unfortunately corrupted our transmission on its way down. Take a look at this received sequence. One of our bits has somehow flipped to a 0. So when the receiver gets this data, it goes ahead and recalculates the even parity for those P positions using that exact same take and skip logic. But this time, P1 and P4 completely fail their even parity conditions. When we put the check results together in order, so that's P8, P4, P2, and P1, it gives us a binary error sequence of 0101. So what does 0101 actually mean for us? Well, if we take that binary code and convert it directly into a decimal number, by adding the 4 value and the 1 value together, we get exactly 5. And that brilliantly pinpoints the exact location of the corrupted bit. The error is sitting right there, plain as day, in position 5. Honestly, this is the true magic of the Hamming code, because we know with absolute certainty where the error is. We literally just take that 5th bit, flip it from a 0 back to a 1, and miraculously, our original data is restored perfectly. No retransmission required whatsoever. Let's quickly summarize why this math from the 1950s absolutely still matters today. The biggest pro? It's highly efficient for single-bit correction. It's just incredibly elegant. Now, the main con is that sending all those extra parity bits does require a higher transmission bandwidth, but the reliability it gives us is just so crucial that Hamming codes are still heavily used today in satellite communications, modems, and embedded processors all around the world. Thank you so much for joining me today. If you found this explanation helpful, please go ahead and subscribe to Kognito Key, and make sure to like and share this explainer with your fellow learners, because it really does make you wonder just how much of our entire modern wireless world is being quietly held together by a few redundant bits of clever math.